Greetings, M squared here. Today we are going to talk about vertical motion and quadratic equations. So vertical motion would be anytime you drop something from a high place, or any place actually, you drop something, gravity pulls on whatever objects. That's how we're standing on the earth, because gravity is pulling down on us. So you'll learn more about this in science, but we talk about it a little bit here in the Quadratic Functions chapter. So there's a little formula that could actually help us predict how long it's going to take for something to fall. But we would also use these anytime you're shooting anything. If you have a catapult with a watermelon on it and you shoot it in the air, it's going to make that little quadratic curve, right? Remember, that's going to open down. That's why in our quadratic function we have a negative a. Notice this is our quadratic function. It's a special formula for all vertical motion problems. So h is going to stand for height. So over here it kind of tells you what everything stands for. H stands for height and t stands for seconds. So this h of t is saying what is the height at t seconds. So we can use this formula to figure out how long it takes something to hit the ground, at what time it's going to be at a certain height, all sorts of things related to height in seconds when we're throwing something or dropping something. So let's just look at this formula, the negative 16. So here, this is kind of our average acceleration as you drop something. For a while, it gets faster as it drops, and then it stops getting faster and goes kind of at a steady. But this is it almost steady as our parabola, it kind of goes like this, and then it as it goes down. So it depends on how high up you are, on whether that acceleration is getting really fast or slowing down. So negative 16, so that's our number that will always, 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 always be there in this vertical motion problem. If I should say you're talking about feet. There's also one, I think it's negative 4.9 if you were talking about meters. But since we're in the USA, we're going to talk about feet. But if you were in a different country, this would be 4.9 if you're talking about meters, negative 4.9. When we look at this, we've got some variables that we need to figure out because we have to have numbers there. And what number would you put in here? V sub 0. Some formulas you're just going to see a V, but that's velocity. Velocity, and it's sub 0, that means at time 0. So the initial velocity is what we're talking about here. How fast was it going when it was hit? So for example, if I'm hitting a tennis ball, I've got some pressure behind that. So its initial velocity is not going to be 0. Whereas if I drop something at time 0, it's going to be 0. So this will be given to you. This is the basic form. So you're going to be given the initial height, you're going to be given the initial velocity, and you'll have to find out how much time or how high it is at a certain time. So that's kind of what we're working with. We'll go through some examples and I think you'll catch on kind of quickly. But this formula, and I won't make you memorize it, I'll give it to you, but this formula is going to be used in all our vertical motion problems. So velocity tells you how fast an object is going and also what direction it's moving. We learn in science, it's not just about the speed of something. Velocity is telling you how fast and the direction. So if I was moving down and drop something, this might be negative. But for our purposes, we're always going to have velocity positive because it's telling you direction and speed. So this little graph here is from our book, but I want you to see that something is being dropped from a helicopter. And the initial height is 350 feet. So if we were making an equation, right? Then we would put 350 right there. Now, before I dropped it, obviously its velocity would be 0. I'm not throwing it, I'm just dropping it, so it would start at 0. And notice what happens after 1 second, after 2 seconds, after 3 seconds. Can you see how between 1 and 0, there's not as much space, but then it kind of gets bigger? That's what I mean. That's what the quadratic part. But when that 16 is the average velocity, and so you can see that it keeps getting bigger, but eventually it's going to hit the ground. You can, if you have these points, actually come up with an equation. But all we need is this 350, the initial height and the initial velocity, and we can plug it in that equation. So in class, we're going to talk about some other things, but let's look. Initial velocity is 0 because it was just dropped. The initial height was 350 feet. Well, we're going to use our equation, okay, this is important, feet per second. So we're going to do velocity in feet per second. So we're going to use our equation to write a formula. So we're going to say h of t, that's the height at time t, equals negative 16t squared. Remember, that is always, 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 this negative 16t squared is always going to be in our vertical motion. Since I have 0, I'll just put it here, but since I have 0t, that's just going to go away, right? I don't really need that, plus 350. So if we take our calculator and we actually we could find out after 3 seconds what's the height. Now we know here in the picture it says 206 feet, but let's see. If we get our calculator and we say negative 16t squared, that's our time squared, and we said 3, we're going to find h of 3, so 3 squared, and then it says plus 350. So let's see what happens. We get 206. What? Look at that, 206. You could go back and put 4 seconds. Let's see, 4 seconds. What do we get? 94. Okay, so we're a little bit off. But can you see how that formula is kind of cool? You can actually see how long it would take for something to drop. So our h of 3, what was that? 206 feet. And it says, is that close to the graphic? And we already talked about that. We'll do these notes in class too. Let's try another problem. So now we're at a diving board. So I don't know if you've ever been diving at a swimming pool, but sometimes people just step off. Sometimes they jump up. And you can kind of see if this person's jumping up or diving, you can see that parabola, I should say. So when we look at this picture, it says, what is the initial height? Well, we can see that this was the start, 30 feet. Now it looks like he didn't jump up. Looks like well, maybe he just flipped his legs up, right? Looks like he's not doing much there. So we're going to say our initial height is 30 feet and our initial velocity is 0. And remember, we've got this, initial velocity. Sorry, I should read the problem. A diver jumps off the platform at initial velocity of 16 feet. So he is jumping up. It helps to read directions. Okay, so what is the function that represents it? So we got to go back to this and we're going to fill in what we know, right? Our v sub 0, this is our h sub 0, that means the height at time 0, and this is our v sub 0, which is our velocity at time 0. We're going to write our equation. So h of t equals negative 16t squared, which is always there, plus 16t plus 30. That is our equation. And then we can, if we have that equation, we can answer a whole bunch of questions. It says how many feet above the platform with the that's probably supposed to be, will the diver be at the highest point of his dive? Now, this is where the information that we learned last section is going to come into play. What do we call this highest point right here? Hopefully you remembered it's called the vertex. That's right, the vertex. We have to find that. Now the vertex is going to give us an x and a y. In this case, it's going to give us a t and an h sub t. If we know the vertex, we know how long it took for the person to reach the highest point. How do we find that? Well, we use our formula. Remember, we just learned that x equals negative b over 2a is my axis of symmetry, which is also the x-coordinate on my vertex. So I'm going to find negative b over 2a for this function. Let's do it. The opposite of 16, this 16, the b, remember this is b, this is a, over 2 times a. Right? Well, that cancels. If you don't like that, you could have multiplied it out. Negative 16 divided by negative 32 is 0.5 or a half. Either one. So we know that it took a half a second for the diver to reach the highest point. But we want to know what the highest point is. So we're going to find h of 0.5. We're going to plug 0.5 back into that calculation right there. If you want to use fractions, you can. Real quick, if you use fractions, a half squared is a fourth. So I would have 16 times a fourth plus 16 times a half plus 30, but you could also put that in your calculator. So a fourth of 16 is 4, half of 16 is 8, plus 30, so 30 plus 12 is 42. So we know now that 42 feet is the highest that that diver got, and it took him a half a second to get there. So our vertex would be 0.5 comma 42. Find the diver's maximum height above the water if he dives from a 20-foot platform and his velocity was 8 feet per second. Okay, we can do that because we just make a new function. We say h of t. Remember, what always goes is the negative 16 t squared when we're talking about feet. We know that the platform was 20 feet tall, and we know that the initial velocity was 8 feet. And it says, find the diver's maximum height. That's the y-coordinate of the vertex. So here I go again. X equals negative b over 2a, right? That's our axis of symmetry formula. So the opposite of 8 over negative 32, which is 1/4. 8 goes into 32 4 times. So, or, right, we can say 0.25. And then we plug that back in. We find h of 1/4. And when we do, we get negative 16. 1/4 squared is 1/16 plus 8 times 1/4 plus 20. Again, use your calculator if you want to. Negative 1 plus 2 plus 20, so that's 21 feet. So at a quarter of a second, they would have been at 21 feet. And you can always write it as a vertex, as a coordinate, 2 coordinates, a point I should say, if you would like. So it's kind of cool how you can find stuff out like that. Let's do one more, and then you're off to the races with your homework. So this one's about baseball. It says, Paul hits a baseball straight up into the air. The baseball is hit with an initial velocity of 70 feet per second when it is 3.5 feet off the ground. Obviously, we don't hit a baseball when it's on the ground. We hit it, right between with the bat. So it's 3.5 feet off the ground. So what's the initial velocity? What's the initial height? The initial velocity is down here, feet per second. What's the initial height? 3.5 feet. What quadratic function models this? Let's look. We've got to use our function h of t equals, this part's always the same, and then we have initial velocity, which is 70 t, and then our initial height. Remember, t stands for time in seconds, h stands for height, and h of t is the height after t seconds. So they want to know after 2 seconds, where is the ball? That's what h of t means. What is the height after 2 seconds? So I would take my negative 16 and I would put my 2 in for that. That's what I'm doing here. And again, use a calculator if you like. 2 squared is 4. 4 times 16 is 64. It's negative 64 because that 16 was negative. Plus 140 plus 3.5. Now we would anticipate a baseball going high up in the air. So what do we got? This is 76 plus 3.5, so 79 point, what do we got? 0.5, sorry, I was confused for a minute. Yeah, so that is how you do that. Now, can you graph it? Can you graph that equation? Well, we can, because we know what's happening at 2 seconds, and we can figure out the vertex and the axis of symmetry. So let's figure out the axis of symmetry. So we get x equals the opposite of b over 2 times a. So we get negative 70 over negative 32. So those are going to both cancel out. Let's see, I'm over here on my calculator. 70 divided by 32 is 2.1875. So at little over 2 seconds, we know that that's going to be the vertex. Would help if I showed you the graph and the work. Okay, that's our vertex. X coordinate. Now we've got to find h of 2.1875. We're going to use our calculator for that. So I'm going to write the formula, the negative 16 t squared, but instead of t, I'm going to write 2.1875 because that is my x, the seconds that it takes to get to the height, the highest point of the baseball curve. We're going to square that. And then we're going to say plus 70 times 2.1875. and then plus 3.5, because that's the initial height. 80. Okay, so our vertex is 2.1875, comma 80. Now, if we wanted to just estimate, we're going to say 2.2 and 80, right? That's going to be our vertex. So let's talk about, whoops, I'm moving my camera. Let's talk about why everything is just in this X quadrant, the first quadrant, I should say. So here's time, 1, 2, 3, 4. You know what? Maybe I shouldn't count by ones. Maybe I'll count by halves because we have some points there, so it might be easier. So I'm going to count every half. So 2 lines is 1, then 2, then 3, then 4. Okay, how long is it going to take that baseball to hit the ground? And what about height? We don't want to count by ones. It's going up to 80 feet. The highest it is 80 feet. So I don't want to count by ones. So maybe I'm going to count, you know, like, let's see, we can count by fives. I think we'll be okay with fives. 5, 10, 15, that's 20, 25, 30, 35, 40, 35, 40, 45, 50, 55, 60, 65, 70, 75, 80. Okay, so here's 80. We know it goes to 80. So after 2.2 seconds, so I'll come over here to 2, that's 2.5, so it's going to be right in here. This is going to be the highest point. We know it starts at 3.5 feet, so that's going to be right here at time 0. And we found that at 2 seconds, it's at 76, so that would have been right there. And we know since it's a parabola, it's going to be, you know, going like this. So we could find one. Let's look. Let's look. It's just kind of fun to play around with it. We can, remember in class we talked about patterns, but you can't use a pattern when, well, we could with the 16, couldn't we? We could actually use a pattern. I didn't even think about the 16. What would our pattern be at 16, guys? That'd be fun to try to do. Okay, it would be 16, and then, so at 1 it's 57. So 30, 40, 50, 60, so right in here at 1 second. And then we know that over here would be the same. And we could just draw it like that. And you can kind of play around with it. It's kind of cool. You can, now that I've took the decimals out, you can kind of just change that. Well, what about 4 seconds? Let's change the 1 to 4. What would happen at 4 seconds? Well, it's 27. So let's look. So 27 is right in here. Well, what about 5 seconds? Is it going to be on the ground or not? Let's look. Has it already touched the ground at 5 seconds? Let's check it out. Ooh, it has, because now we got a negative 46. Well, remember, this is our formula for height. The ball can't be negative 46 feet. That means somewhere between 4 and 5 seconds it actually hit the ground. Now, if you graph this using technology, you would find that exact place where it hit the ground, but we just know that it's going to be somewhere between there. And you could keep playing with that, 4.5, and keep going on for quite a while. But this is our picture. And it really, when you have the graph, the reason we really stay in that first quadrant is, well, number one, we don't want to have time that's less than 0. Can't have negative 3 seconds. And we can't have the ball underneath the ground continuing to go. Because once it hits the ground, gravity has stopped pushing it forward, and it's just going to stay there. So those are the vertical motion problems that we're going to do. You'll have a few more to do for homework. Keep in mind this formula, the negative 16t squared, and that t always stay the same. Initial velocity goes here, initial height goes here, and you can plug in any second you want to find the height at that time. It's kind of cool. All right, good luck. M squared signing out.